Today I'd like to present an introduction to nomenclature of stereoisomers. This is part 2 in the stereoisomer nomenclature, and we'll be using the Cahn-Ingold-Prelog rules to assign R and S configurations to stereocenters and EZ configurations to alkenes. From the previous video, you should already be able to assign priorities to a stereocenter. So in the example given here, you should already know that the cyano group is the highest priority, the amine is second, the alkyne is third, and the hydrogen is fourth. Now once you have those priorities assigned, it's important to rotate the molecule so that the number 4 substituent is pointing away from you or back into the page. So on the molecule shown, I know that I'm going to have to rotate so that the number 4 priority is in the back position. Now the number 3 group is there right now, so I know that's going to have to rotate as well. When you rotate around an sp3 hybridized bond, 3 groups are going to move. So I can either keep the number 2 group still and rotate 1, 3, and 4, or I can keep the number 1 group still and rotate 2, 3, and 4. So for this first example, I'm going to keep the number 2 substituent right where it was, and I'm going to rotate the 4 to where the 3 where the 1 is, and the 1 where the 4 is. So that's the rotation that I'm doing, and I'm doing that by rotating around the carbon-carbon bond to priority number 2. So let's clean that up and redraw it. The number 4 substituent is going to be back. That's going to push the alkyne out of the way, so I'm putting it forward, and the nitrile will be up if I keep the amine still. Now of course another option would be to keep the number 1 group still and rotate 2, 3, and 4. So the number 4 group is going to have to go back, the number 3 group will go on the side, and the number 2 group will go on top. Again, cleaning it up a little bit, let's take a look. I have the option of keeping the nitrile still. Number 4 group has to go back, the other 3 groups must move. So I can use either of those methods to rotate the molecule to determine the absolute configuration. Just to get it all on one screen, it would look like this. So either of those rotations is perfectly fine. Now once you have the number 4 group back, if you look at groups 1, 2, and 3, if they proceed in a clockwise direction from 1 to 2 to 3, it's an R stereocenter. And if it proceeds 1 to 2 to 3 counterclockwise, again with the number 4 group back, it's an S stereocenter. So looking again at our molecule and putting our priorities back on, we said that we have 1, 2, 3, and 4. That means that 1 to 2 to 3 with the number 4 group back is counterclockwise. So this particular stereocenter has an S configuration. In this example, I have an alkyl halide, and we should already know how to name alkyl halides other than the stereochemistry. So this would be 2-bromo, 3-chloro, pentane. Now I need to go back and look at both of those stereocenters and determine whether they're R or S because the geometry is very clearly specified. So let's look at the C3 first. It's easiest simply because the hydrogen is already back and the number 4 group is that lowest priority hydrogen. Looking at the stereocenter, I compare a chlorine as 1, a carbon to bromine as 2, and a carbon to carbon as 3. In other words, I have a carbon bonded to C, H, and H for the 3rd priority group, and on the other side I have a carbon bonded to bromine, carbon, and hydrogen. A CBr is higher in priority than a CC. So if I want to determine the stereocenter at C3, the number 4 group's already back. 1 to 2 to 3 is a clockwise motion, and this has an R stereochemistry at C3. So I'm going to write over here R at C3. Okay, cleaning up the structure a little bit so that I can go back now and look at the stereocenter at C2. The H that is not shown is pointing out. It is going to be the number 4 substituent. Bromine is number 1. A carbon to chlorine is going to be higher in priority than a carbon to hydrogen. I need to rotate so that the number 4 group is back. And it might be easiest to kind of just get rid of the atoms for a minute and say, okay, If I want to rotate, what I usually do is put the bonds in exactly the same spot. Pick something that will stay still. 2 or 3 can stay still. Number 4 has to go back, so it moves. Number 1 is back, so it moves. Number 4 group must be back. I'm going to keep the number 3 group still, which means 1 rotates into the plane and 2 rotates pointing out. 1 to 2 to 3 is a counterclockwise motion, and so it is S at C2. So to represent the stereochemistry, I simply put 2S, 3R in front of the name of the alkyl halide. The 2 and 3 specify which stereocenters have the R and S configurations. Those are set in parentheses. There's a comma between 2S and then a space and 3R, and hyphens between numbers and letters, or parentheses and numbers. So let's take a look at the alkenes. The simple alkenes can be named as cis or trans. For the cis alkenes, the substituents are on the same side as are the protons, and for the trans alkenes, the substituents are across from each other, as are the H's. When the alkene is more complicated, in other words, there's not one hydrogen on each of the 2 carbons bonded in the alkene, then we have to use the E and Z nomenclature. To apply the E and Z nomenclature, we first consider the substituents on one side of the alkene. So the red squiggly mark is meant to separate the left side from the right side of the alkene for our comparisons. On the left side, the higher priority carbon is on the top and the lower priority hydrogen is on the bottom. On the right side, we have the same thing. Therefore, the higher priority groups are on the same side of the alkene. In this case, they're both up. And this is a Z configuration. For the molecule on the right, I have the higher priority methyl group on the top left, and I have it on the bottom right. These are across from each other, so you can either say that the higher priority groups are across from each other, and that's opposite or trans, it's an E configuration, or you can compare the higher to the lower on the same side of the alkene and say, well, those are opposite, so this is an E alkene. So let's take a look at this alkene and determine whether it's an E or a Z configuration. Again, I'm comparing one side of the alkene to the other. So on one side I have a carbon bonded to 2 carbons and a hydrogen. And the other group to which I'm making a comparison is bonded to a carbon and 2 hydrogens. So CC is a higher priority than CH. So I have my higher priority group on the top and my lower priority group on the bottom. Looking at the other side, I have a CH2 to a CH2 that's tied, so I keep walking out the chain till a point of difference is made. Here I have a carbon bonded to 3 hydrogens, whereas here I have a carbon bonded to a carbon and 2 hydrogens. So the CC is a higher priority than the CH, so this is high, this is low. They are across from each other, so this is going to have an E configuration. Now once you learn how to name the alkenes, you will see how to write out the nomenclature for this molecule. It is E, 4-ethyl, 5-isopropyl, oct-4-ene. That is all one word with no spaces. In summary, the stereocenters are named by first prioritizing the 4 groups that are attached to an sp3 hybridized carbon. Once you have the number 4 group rotated to the back, moving from group 1 to 2 to 3 in a clockwise motion would classify the stereocenter as an R configuration. 1 to 2 to 3 counterclockwise is an S configuration. When using the Cahn-Ingold-Prelog rules for alkene nomenclature, first, you'll want to compare the substituents that are bonded to the same carbon and rank them as either high or low, and then compare across the double bond. If the highest priority substituents are on the same side of the molecule, it's a Z alkene, and if they're on opposite sides, it's an E alkene. Here's some examples for you to try. Pause the video, try to classify the stereocenter as either R or S, or the alkene as either E or Z, and then come back to the video to see the solutions. Taking a look at the first problem, I'm comparing a chlorine to a carbon to a deuterium to a hydrogen. Chlorine is the highest priority, carbon is second, deuterium is third, the proton, hydrogen, is fourth. The number 4 group is already back. 1 to 2 to 3 is in a counterclockwise orientation. This is an S configuration. That one's pretty straightforward. The second problem is not as obvious. First of all, on the glancing at the molecule, I noticed that I have 4 carbons bonded to the stereocenter, so I have to march further out the chain to figure out which is the highest priority. Here I have a carbon bonded to a carbon and 2 hydrogens. Here I have a carbon bonded to 2 oxygens and a hydrogen. A carbon bonded to an oxygen and 2 hydrogens. And that's a carbon-oxygen double bond, so I have a carbon bonded to 2 oxygens and a hydrogen. So what I see is the lowest priority group is the CH2 as part of the longer alkyl chain, and the number 3 priority is going to be CH2OH. And I need to consider the aldehyde and the acetal a little further. Moving out the chain a little bit, I now have an oxygen that is bonded to a carbon, and that's it. Here, I have an oxygen that's bonded to a carbon, but then the chain continues. So after the oxygen, I then have a carbon bonded to 3 hydrogens. There's more atoms here. In other words, I ran out on the aldehyde. So this acetal is going to be the highest priority, and the aldehyde is the lowest priority. Again, the number 4 group is already rotated back. 1 to 2 to 3 is counterclockwise. This is an S stereocenter. Looking at the alkene, remember that I'm comparing the left-hand side of the alkene to the 2 substituents to each other and the right-hand substituents to each other. On top I have a carbon bonded to a bromine and 2 H's. And on bottom I have a carbon bonded to 2 carbons and a hydrogen. CBr is higher in priority than CC. So I've got the methyl bromide group as highest priority, and the larger substituent is actually the lower priority group. For the other side of the alkene, I have a carbon double bonded to an oxygen, so the oxygen counts twice, and a hydrogen. And on the alcohol portion of the molecule, I have a carbon bonded to an O18 and 2 hydrogens. Carbon to O18 is going to be higher priority than a carbon to O16, and so this is my high priority group. My low priority group, they are opposite from each other. This is going to have an E configuration. And I used both the Wade and McMurray textbooks for preparation of this presentation.